up here we have kind of what I put up here yesterday, algebra versus calculus, right? This concept of slope, very similar, but in calculus we're doing the slope of 1 point as opposed to 2. It's the slope of a tangent line to a curve as opposed to a secant line with 2 points. It's instantaneous rate of change instead of average rate of change. Again, the rest of this year, when you hear average rate of change, you think slope between 2 points. The word average in this class doesn't have anything to do with adding up a bunch of stuff and dividing by how many there are. That's not the average we're talking about. It's not like stats class where we're looking for the mean or something like that. We use the term mean as in average, but it doesn't mean the same thing. Okay, so average rate of change for us is this point, this right here, slope between 2 points. So when you hear average rate of change, you're always thinking slope between 2 points. Okay, and in algebra class we usually write it this way, but we could write it this way. We could write the 2 points instead of A and B. We could write A and A plus H. The only difference is there we're using H as the run, so A and then the run, and the second point be A plus H. It just makes it nicer in calculus for us to do it that way because we focus on the run, H, going to 0, and we can bring in the limit. And then we talked about yesterday the difference quotient with the limit, because often the definition of derivative is often talked about as the limit of the difference quotient, right? The limit of the difference quotient. But it's this, and again, those two things. This is slope between 2 points. This is the 2 points becoming 1. Okay, so this would be an estimate of the derivative if you pick 2 really close points. So earlier this year, we were picking 2.0001 and 2 and doing the slope. That's an estimate of the derivative, right? But when you bring in the limit, and Alan asked the question yesterday, can you actually get a value if you're just saying H is approaching 0? And the answer we found out, yes, you can. It's what that slope is approaching. That's the answer you get, and that is the exact slope, the exact derivative when you do the limit as H approaches 0. So you put in a really small h, 0.001, you're getting an estimate of the derivative. If you let h go to 0, you're getting the exact derivative. Important to understand that difference. Okay, so we have this picture. So the 2 points becoming 1 by letting h go to 0. Now there's another way we could write it, and this might be worth putting in your notes if you want to get your notes out right now. We're going to get into some homework questions here for sure. 34 and 35 would be good ones to do, maybe. Okay, looked like a lot of you did a pretty good job on 41 through 44, number 7. I mean, as I was looking through there on the homework, looked like there was you had written out your work. Things were looking pretty good there. But we'll go through that a little bit. Maybe not every one of them. Of that section, which one would you want to see for sure, 41 through 44? 44? I think 44 is worth looking at. Probably the algebra in there. We're going to focus today on several algebra techniques. The one we did yesterday was pretty much FOILing, factoring, canceling. That one's probably the easiest of the algebra techniques that we do. 44 got into a little, some other stuff there. But here's another version, and all it is different notation. Okay, and it's not really as user-friendly, and it's kind of limiting, as you'll see what we do today. But this would be more like the f of b minus f of a thing. Okay, but here'd be another way to find the slope at a. Notice it's exactly the same picture. I mean, if I go back, you can hardly tell the difference between these two slides. If I go back, I mean, they're almost exactly the same thing, right? I mean, all I've done is call my second point x instead of a plus 8. So I said, okay, let's let the second point be x. First point is still a. I'm still trying to find the slope at a, okay? And all I did is call my second point x instead of a plus 8. So what's the difference? Well, this second point is still going to get closer and closer to that point. So the limit now, instead of letting h go to 0, let me go back. Instead of letting h go to 0, because that's what happens here, as this point gets closer and closer, the h is getting smaller and smaller. So instead of do the limit of that as h approaches 0, we do the limit as x approaches a. So the limit as x approaches a, and then it would be your y subtracted. Well, if this is a, that's f of a. If this is x, that's f of x, right? The outputs. And so it'd be the y subtracted, be f of x minus f of a, and then that right there. So what would that look like? Well, in this problem, let's say we had, let's just do a quick example. I'm not sure if you might have had one like, no, I don't think so. I think I took that one out of the homework. So let's say we had f of x equals x squared, and we wanted to find f prime of 3. Right? What would I set up for this one? F prime of 3 would equal, tell me what to write. Limit as h approaches 0. I just noticed f of 3 plus h, f of 3 over h, right? And then how would I go through that? I would plug in my 3 plus h, so it would be 3 plus h squared minus 9, and then all over h, it would be 9 plus 6h plus h squared minus 9 all over h. 9's canceled, take out an h. I do 6 plus h all over h. H is canceled. And I get 6 plus h, let h go to 0, I'd get 6. Bingo, right? Just like that. So that's what we were doing yesterday. All right, what would it look like in this scenario? Same problem. F of x equals x squared. F prime of 3. Well, f prime of 3 would equal limit x approaches, what's a? 3, right? A is that number right in there, right? So a is 3. F of 3, no. F of x minus f of 3 all over x minus 3. Okay? So now, limit x approaches 3. What's f of x? X squared minus 9 all over x minus 3. Now what can I do to that? I can factor the top, x plus 3, x minus 3, all over x minus 3. Cancel. I get limit as x approaches 3 of x plus 3. Now how do I get that? What does that answer, do you think? 6. Now see up here, plugging in a 3 was a problem, right? Because you plug in a 3, what happens? Divided by 0. That's a problem, just like in the other one. But when you cancel, all of a sudden that problem goes away. Now what's x plus 3 as x gets close to 3? Well, if x is 3.001, this would be 6.001, right? But as it gets closer and closer to 3, this is getting closer and closer to 6. And so the answer would be 6. And of course, that was the same answer, right? Just an alternate version. It's just, because again, look at the picture. It's the same thing. It's 2 points becoming 1. It's doing the slope with 2 points becoming 1. It's just different notation. Now, I say that, we don't hardly ever see this version of the derivative, okay? Don't hardly ever see this version of the derivative. But I know on one of the multiple choice questions in one of our practice packets, might even be on one of the midterm or final questions, where they give you limit as x approaches 2 of, or maybe it's pi, and then they say sine x minus sine pi all over x minus pi. And they want you to do that problem. And it's a no calculator. And it's like, oh my God, I can't do that. I can't do that problem because here I could because I can factor and cancel, right? I can factor and cancel. But I can't. There's nothing to factor and cancel there. But actually, and if you try to plug in a pi, you get 0 divided by 0. But what you're supposed to do, and this is what 34 and 35 are actually about, which we'll get to in a minute. But what you're supposed to actually do on this problem is you're supposed to recognize that as, oh, that's a derivative. That's the derivative of what? F of x. What's setting right there? What's setting right there in that one over there? Sine x. So what this problem really is the derivative of sine at pi. Well, what's the derivative of sine? We already know that. It's what? Cosine. And what's cosine of pi?
0.
No.
Cosine of 1.
Cosine of pi is -1. Pi is over here, the x coordinate, cosine, -1. Right? -1. So the answer to that problem is -1. That's how you get it, is you look at that and you recognize, you say, oh yeah, that's the derivative. That's slope. That's 2 y values subtracted, 2 x values subtracted, and divided as x approaches pi, as the 2 points become 1. That's derivative, and that's what you're supposed to recognize. Now, to be honest, when we do that, it might be January or something, and we haven't seen it since today, and you're going to be like, and then I'll remind you, that some of you will be like, oh yeah, and then some of you will still be like, and then you'll, maybe. All right. So, here we go. Here's a problem we kind of did yesterday. Don't write any of this down. This is just stuff. This is just, right, f of 2 plus h. So we're going to stick with this version. Okay, we're going to stick with this version because you're going to see today, this one's limiting because this only lets us do the derivative at a point. What we're going to do today is we want to find a way to do the derivative at any point. A derivative formula. Okay, and that's what we're going to come up with today. A shortcut, and it's pretty cool. All right, but anyway, so we go through, we get all this, and we got that. And we talked about how f of 1 is that, f of 5 is that, f of z, you plug in z, f of peanut, f of peanut, you plug in a peanut, right? F of German short hair, you plug in German, f of 2 plus h, you plug in the 2 plus h everywhere. Okay, so here's the one we did yesterday, we got 70. All right, this problem, any questions on any of those? This was what, 13, was that section 11, 12, 11, I guess. I guess 11. Any questions there? 11C. Estimate the instantaneous rate of change. So, average rate of change, you find the first point, the second point, like between, I know you didn't even ask about this, but I can't help myself. Okay, 8 a.m. is this point, and 2 p.m. is this point. The average rate of change is that slope right there, right? You just subtract. Now, you're subtracting time, so that would actually be not 2 take away 8, but it would just be 6 hours, right? So that'd be 6 hours, and then whatever that rise is, right? So just rise over run, okay?
Just a general question. So, like, for the limit, is that just supposed to make you put 0 in so you don't put in an arbitrary value? Or,
what do you mean put 0?
Like, for instance, like, limit h approaches 0. Like, does that just force you to put 0 into that?
Just like here, it forces you to put 3 in, right?
Yeah, so it
yeah.
forces you to put 3 in instead of like 4 or like 5.
Well, right, because that's what, the question is, what is, the question, we're going to do this more in a few days, but the question is more, what is this value doing as this input goes towards that? So that's why you want to put that in. Problem is, in most limit problems, if this actually equals that, bad things happen. Like you're dividing by 0. Something weird's going on. Okay? So what we need to do is somehow manipulate it to see what it's approaching. Okay? All right. So anyway, we'll get more into limits later. All right. So, Gloria, to answer your question on 11C, the instantaneous rate of change at 9:15. Well, this would be 9:15. So here's what they wanted you to do is draw in that and then just do a rise over run. Because instantaneous rate of change, whenever we hear that, instantaneous rate of change, we're talking about slope at one point. Okay? And I don't, what did the back have on that one? 11C, -4. Okay, somewhere in there. Okay, so what was that? 11C, yeah, -$4 per hour. It'd be good to put some units on that. Okay, so I had that on there. Okay, just in case anybody had some questions. All right, here was what number was this? This had was this the very next one? Was this 13? No. Is this one of them? Why do I have this on here? $13 was not that. It was like that though, right? But it was a different function. Why do I have this on here? Is that 12? No. Does that look familiar at all? It's just like 13, right? It's just like 13, okay? So, I don't know why. I don't know. this one is talking about where they give you an h, and then, so that's just they give you a real small h, and so that's just your 2 points, right? And so that's all you had to do on 13. So be 3.01 plugged in, and then a 3 plugged in, and then do your slope, okay? And then when you have a table, just pick 2 really close values, pick the 2 closest values you can, okay, that kind of thing. I want to wait on 34 and 35. So I was going to look at 43 maybe, 40, I have 44 up here, so we're definitely going to do 44. But is there any value in doing 43? Some of that? Let's set that up. So that'd be the limit as h approaches 0. The function is what, x cubed? There is a reason I want to look at 43, I guess, that'd be valuable. And so this would be f of, and where are we doing the slope at? 4. So f of 4 plus h minus f of 4 all over h, right? So far so good. So now this would be 4 plus h cubed minus 64 all over h. Okay, so I wanted to talk about 4 plus h cubed. Now, I don't know what you guys did last year, how much of this you did last year. Do you remember something called Pascal's triangle? Did you guys look at that last year? Now, you don't need to do it, but this is Pascal's triangle. It's got kind of a cool little pattern there, right? And it's got a lot of different uses and so forth. One of the uses is doing a binomial cube. Now, one way to do 4 plus h cubed is do 4 plus h times 4 plus h times 4 plus h, right? And so 4 plus h times 4 plus h would be 16 plus 8h plus h squared. And then you got to take that times 4 plus h, right? And how do you do that? Well, you take the 4 times everything, take the h times everything, and then you add them all up. Okay, and that's fine. Just go ahead and do it that way. Now, Pascal's triangle can actually be a shortcut of that. Because this row, because what Pascal's triangle gives you is the coefficients of a binomial expansion going like that. So x plus y to the 0, of course, is just 1. X plus y to the first is 1x plus 1y. X plus y squared is 1x squared plus 2xy plus 1y squared. And x plus y cubed is 1x cubed plus 3x squared y plus 3x y squared plus 1y cubed. See the pattern? So it's the first thing cubed, then squared, then to the first, then not at all. And then it's the second thing, the y, not at all, then y to the first, y to the second, y to the third. And then the 1, 3, 3, 1 is the expansion. So if you have to do to the 4th power, to the 5th power, Pascal's triangle can be really, really handy to do an expansion. It's just a little shortcut. If you know it, want to use it, go for it. So we could do that here. So we could say, okay, this is going to be 1, 4 cubed, which is 64, plus 3, 4 squareds, right? 3, 4 squareds. What's 4 squared? 16. What's 3 times 16? 48. And then h to the first, plus 3 4s, which is 12, h to the second, and then 1 h cubed. Okay? So that's just a way I can do a cubic a little quicker. Okay, so I got these coefficients, and then it's the first thing cubed, and then squared, and then the first, and so on and so on. Okay? All right. So anyway, the 64s cancel, but you can work it out this way, you get the same thing. All right? Now we can take out an h, and so we get 48 plus 12h plus h squared all over h. And now we let h go to 0, and what do we get? 48. That seems like a big slope. But it is x cubed, and x cubed goes up really fast, and by the time you get out here to 4, it probably is really steep. Okay, so it probably is. Okay, so I wanted to talk a little bit about that expansion, because that's going to come in handy here a little bit. Okay, all right, let's stop just a second, and let's just talk about this real quick. You don't have to write this down or anything, but let's just think about this. How many different ways, if I gave you this, let's say you had your calculator, how many different ways could we find f prime of 1 if I gave you this function now? Find or estimate f prime of 1. Well, give me one. It's the very first one.
The average.
Pick two really close ones, right? 1 and 1.001, plug them into a slope, right? That's one. Okay, what's an obvious one that we just had? The limit definition, right? The definition of derivative. What would be another one? Think graphically. Do a graph and try to do a graph and then put it on my paper and then estimate, draw a little tangent line, kind of be right over right, that kind of, right? Those are all the different ways right now we can think of that we can do a slope, where we can find f prime 1. Now, our goal today is to find some formulas. Wouldn't it be nice if we said f of x is equal to x squared minus x, and then we could say f prime of x is some little formula with x's, and then we can just plug a 1 into that, and get that, instead of doing the whole limit definition. Well, that's where we're going to head here. Okay, so what else we got for questions? 44 probably, and then 34 and 35. Okay, all right. So you got your notes out. So before we do that, let's jot down some notation here. Let's jot down a little bit of notation. Kind of jumping around a little bit, but that's okay. It's all kind of the same thing. All right, let's talk about this a little bit over here. Okay, so all right, so over here on this corner. So our typical function notation we've been using so far is this. So let's say we have the function f of x equals sine x, right? And we want to, so we were just talking about what would be cool if we had a derivative formula we could just plug into. Well, we already know one. Well, we actually know a couple. We know that if f of x is sine x, we know f prime is cosine x, right? We already know that one. So if we wanted to find the slope at 3 pi of the sine curve, we could just plug 3 pi into the cosine. And that would give us the slope of the sine curve at 3 pi. So we already know that one. What's another one we know? What's another function where we know its derivative equation? E to the x. It's its own derivative, right? F of x, e to the x. Its derivative is e to the x also, right? So that's another one we already know. Now, there's some other notation we can use, because we don't always have to use f of x. We don't always have to use function notation. We can use y. There's going to be times you're going to see where we use y. Now, y and f of x are interchangeable. Y and f of x are interchangeable. So if we got y equals sine x, we could write y prime. So sometimes we write y prime equals cosine x. It's the same thing. But then we got this new notation down below that, okay? The new notation here, this is called Leibniz notation. One of the co-inventors of calculus, and he used more of this notation. Now, where do you suppose that notation comes from? The idea of what? Concept of what? Slope. Didn't look like slope. It actually comes from the Greek letter delta, a little triangle, which means change in y. This is often used for slope, change in y over change in x, delta y over delta x. That's what slope is, and so we use dy over dx, but so that kind of gives us this concept of slope. Now, there's no division going on there or anything. It's just notation. So a lot of times I'll say dy dx. It's really dy over dx, but just for shortcut's sake, I'll say dy dx. Okay? And the nice thing about that notation is it tells you what it's with respect to. That's why function notation is good, because it tells you what the input variable is. Just like on our calculator, if you see a t in there, you know you're supposed to put a t in. Is the input variable. When you just use y, you don't know for sure always, but dy over dx, that's another way of saying y prime. Think of it as this. Read it this way. Derivative of y, think of that as derivative of y with respect to x. Derivative of y with respect to x. That's what we think of when we see dy over dx. Just like this is derivative of f with respect to x. We always say with respect to, but there are going to be times where we need to know what the input variable is. Strangely as that may seem, you would think, well, we know the input variable. Well, you'll see later in this chapter why that's important. But that's just an alternate notation that shows up something. Okay? Now, Sometimes we don't. It's kind of a pain to write two things. If we want to show that the derivative of sine is cosine, it's kind of a pain to write, okay, y equals sine, y prime equals cosine. So we kind of combine the Leibniz notation. This is where that gets really useful. So if you think about what I've written over here on the right, it's kind of like I've taken out the y. Now look over there at that. It's kind of like I've taken out the y and I've put the sine in its place. Because y is sine in this case, right? So I've taken out the y, put sine in its place. Now I didn't put the sine up on top, I kind of put it up front. But if you think about fractions, we do that all the time. 2x over 3 is the same as 2/3 x. Would you agree? Okay, so I can take that thing that's on top and I can stick it out in front here, or behind, or whatever that you call that. And then it's the same thing, right? So what I've done is I've said, so we would read this as a derivative of sine with respect to x. So the derivative of sine with respect to x is cosine. Okay, then I can put it all in one line. And we're going to actually start making up a list of rules like that. So we would have two in our list of rules that we're going to make. We would have two of those so far, right? We would have those two right there. The derivative of sine x is cosine x, and the derivative of e to the x is e to the x. And those would be two. Actually, we know cosine too. Didn't we look at that? What's the derivative of cosine? Remember that? It was negative sine, wasn't it? So there's a third one, right? There's three rules, derivative rules. And second derivative, of course, we know f double prime is second derivative, or that could be y double prime. But another way to write second derivative in Leibniz notation is with 2's up there. Now, it looks like you're squaring something. We're not squaring anything. What it's really doing is this. When you're doing, the reason it looks like that, again, just like dy over dx, we're not dividing anything. It's just the concept of slope, so we're thinking derivative. The second derivative is the derivative of the derivative, right? So if we think about this notation over here, it'd be like doing this. The derivative of what? Oh, the derivative of the derivative, right? So if you think of that, if you think of it that way, if you think the second derivative is the derivative of the derivative, you can kind of see why it's d squared y over dx squared, right? You got to see where that comes from. So when you see this, people get freaked out. They see this and it says find d squared y over dx squared. Well, it's just saying find the second derivative. Y double prime. Just other notation for the second derivative, okay? That's all it is. All right, so just to start getting used to some different notations. All right, let's move on to 44. Now, what was difficult about 44 was the algebra part of this. So let's talk about that. So I've already started to set it up. And so we would plug 4 plus h into here, so we get 2 over 4 plus h. Would you agree with that? And then minus 2 over 4, which would be 1/2, which we could reduce, but don't have to right now. Okay, so what do I do to that?
You can make them common denominators.
Common denominators. We need to get common denominators. Now, how do we do that? Mrs. Payne always used to call it bow tie. Mrs. Clark call it that? Yeah. Did she? Remember the term bow tie? Okay. And it's fine. You could do that. It's a simple way to do it every time. The downside of bow ties, it doesn't give you the least common denominator, but to be honest, we don't really care. Okay. And it works. Okay. But that's a way to get common denominators. So let me go through it two different ways. So let me first just do kind of maybe a middle school, well, it's not really middle school with algebra, but the concept of common denominators is what goes into both of those. Like if you have x and y, well, the common denominator is x, y. It's a lot of times just these two times each other. Now, it wouldn't have to be if they had common factors. That's where we get into the least common denominator. But to be honest, that doesn't really matter. So one way of doing it is just say, okay, I'm going to take this times 4 plus h and 4 plus h, top and bottom. And I'm going to take this one times 4, top and bottom. Okay, so I'm going to do it this way first. Okay, so that would give me 8 over 4 times 4 plus h, right here. And then this one I would multiply, now it's minus, and then this one would give me, I got to distribute that, so that'd be 8 plus 2h, and then over 4 times 4 plus h. right? So now I've got common denominators. So that means I can now put those together, okay? All right, now the bow tie method would look like this. Let me use black for the bow tie. The bow tie method is a little bit like a cross multiply kind of thing, right? So the only thing you got to worry about is the order. You got to go this way first, right here. Okay, so you take this 4 times that 2, and that gives you 8, minus, then you take this 4 plus h times this 2. Now here's where you also got to be careful, because you got to do parentheses. I didn't worry about parentheses here because I will have to distribute that negative when I subtract over here. So we got to take that 4 times that 2 and get 8. Then we got to take that times that, and that would be 8 plus 2h. And then it's all over that. And that's like the bow tie, right? And so the bottom multiplied together. So that's 4 times 4 plus h. And then all over h. Okay, so that's basically doing the same thing. It's basically, the red and the black are basically doing the same thing. Okay? All right. So then, now we got to distribute here. All right? So we're going to get 8 minus 8 minus 2h. That's the most common mistake people make on this, is they lose track of that negative. So we're going to get negative 2h over, and I could distribute this. A lot of times we don't distribute the bottom because a lot of times we're trying to cancel something, and so leaving it factored is usually a good thing. But if you want to go ahead and distribute it, and then you end up having to factor it later, that's fine. Okay? Now don't forget, this is all over h. That's the other thing people sometimes forget, all over h. Now what do you do with this? Yeah, I usually call it invert and multiply. What you're doing is you've got this divided by h. Well, dividing by h is the same as timesing by 1 over h, right? Dividing by 2 is the same as multiplying by 1/2. So I'm taking this fraction on top and dividing by h. Well, that's the same as multiplying by 1 over h. Dividing by h is the same as multiplying by 1 over h. And now we can see that those two h's cancel, which of course is what we wanted to happen, just like what happened with our factoring business. So now we got negative 2 over 16 plus 4h, and now we can let h go to 0, and so we get negative 2 over 16 because that becomes 0 right there, and that is negative 1. Okay? Now, if we look at what that graph would look like, 2 over x actually looks a lot like 1 over x, goes like that. So if we get out here at 4, we would have a slope that looks very much like it would be negative 1. Okay? You will have to do that. And coming up on our next quiz, there will be some algebra, limit, derivative, whatever, problems where you're going to have to do the factor cancel thing like the other ones were, and you're going to have to do a bow tie kind of common denominator thing, and there's one more you're going to have to do as well that we'll talk about here maybe today. We'll see. All right. Oh yeah, we're going to talk about it right now. All right. So that's it for the homework. Well, except 34 and 35. We'll get back to that. Okay. So let's talk about this algebra. Let's do just a quick algebra review of some of these things, because you can see what's going to happen when we get into here. When we get into this definition, we're going to get into some algebra we've got to be able to deal with. So let's do a couple quick algebra reviews. So your notes off to the side, some more, whatever you want to do, a little algebra review. Let's talk about some algebra review here. So this is the other main one. There's 3 main algebra reviews you're going to need to be able, algebra things you're going to be able to do. One is the factor and cancel business, foiling, factor, and canceling. The other is the common denominator thing. So let's do this one at the bottom first, since we just got into doing it. So the bottom one here is a common denominator. So before we can do anything with this, we need to get the top together into a single fraction. So if you're going to bow tie this, we would take y times 3. So we have 3y. Then minus 2 times x, and then it would be all over what? All over what? X, y. All over those two multiplied together. So you bow tie, so you cross, multiply here, so y times 3, x times 2, and then all over the bottom ones multiplied together. Okay, now we've turned that into a single fraction, and then it's all over x squared. Well, what do we do with that x squared then? We flip it, or I'd sometimes just say invert and multiply, so it'd be that, right? Now this time it turns out nothing cancels. We end up with 3y minus 2x all over, and then you multiply there, that'd be x cubed y, and then you're done. But the idea is you've just changed that. That's called a complex fraction. Fractions inside of fractions. When you have fractions inside of fractions, you want to get that reduced down to just a single fraction. So that would end up being that right there. But that's the bow tie technique. Fraction inside of a fraction, that's what we got. Okay? So, there's that. Now, here's another one. You remember in Algebra 2 class, you didn't want to have a radical in the denominator. Okay? Now, we don't always care about that, but there's an algebra technique of getting rid of that that actually is going to end up working nice in some problems where we can cancel. Something can cancel. Now, on this one, it's not going to cancel. It's just going to end up giving us, get the radical out of the bottom. But when we, and so this technique we're going to use is typically whenever we see a radical in the problem. Now, it could be on the top or the bottom when we do it. But it's using what's called the conjugate. The conjugate is basically if you have a plus b and you multiply it by a minus b, something nice happens. What do you end up with? A squared minus b squared, and the middle terms disappear. And the nice thing about both of those things being squared is now if you have a radical, if you have a square root in the problem, it's now squared, you get rid of the square root. Okay, that's why it's a nice thing to do. So what would be the conjugate of square root x minus 2? Square root x plus 2. So we're going to take that times the top and the bottom. Okay? Now it doesn't get rid of the square root on top, but it gets rid of the square root on the bottom. Okay, so we're going to have 3, and then we're going to have square root x plus 2, which I could go ahead and distribute that. Actually, it doesn't probably matter. A lot of times I don't distribute that because we're hoping maybe something cancels. But let's say we did. It doesn't matter. We can always pull the 3 back out if we have to. And then what are you going to get down here? X minus 4. But again, that idea of doing the conjugate, what that did is it got rid of that right there. Okay? Now, to be honest, I probably could have made up a better problem there. This would be the type of problem we would do with something like that. This is what our problem would probably look like. Okay, let's say we had this problem right here. Okay, this is the type of problem we would probably be dealing with. Okay, and so now what would we do to the top and bottom? We would multiply by root x minus 2 and root x minus 2, right? So we're going to multiply here and here. Now on top, I would suggest, this is where I would say, let's don't multiply that out, okay? That because number one, it'd just be a big mess. So let's just leave that alone. But what's the bottom end of it? X minus 4. Oh, see how nice that was? Cancel, cancel, and we get root x minus 2. That's what's going to happen in our problem. Okay, that's why we're going to want to do that. Because something nice is going to cancel, and then we'll get something like that. Okay? So, that's called the conjugate method. Okay, so bow tie, conjugate method, and then of course our regular factor and cancel stuff. Those are the algebra things we're going to have to do. All right, so now let's go to 34 and 35. Okay, so in 34, they said, now this is, we're going to practice some of this in a worksheet we do on Monday. But it says the limit shown is f prime of a for some function f and some number a. Identify f and a, then estimate the value of f prime a by examining a graph of a different quotient. Well, we'll just ignore that last part for the time being. But so this is like that problem I was telling you is going to show up sometime in January in a problem. We want to recognize that this is the same as this. These two things are the same. Instead of h, we have what over here? Delta x. Same thing. Delta x means change in x. That's what our h is. That's our change in x. So sometimes we use delta x. Okay? What's the a in this problem? usually like to look right there, right? Because it's A plus H, right? So our H is delta X, so doesn't the A have to be 9? So that means in this problem, what we're really finding is f prime of 9. But for what function? What function? It's the, now remember German shorthand. The A plus H gets plugged into the X, into the function for X. The A plus H goes in where the X was, right? So when we go back to this problem right here, the 4 plus H got plugged in right there where the X was. So when I see 2 over 4 plus H, that tells me that, so if I'm working this backwards, which is really what this is, that tells me if I'm looking at this, I'm saying, oh, the function must have been 2 over X. Because the 4 plus H went in where the X was. So 2 over 4 plus H must be 2 over X. Okay? So that tells me in this problem, this must be where the X was. So this function must have been, what did you say? Square root of X. So this problem right here was saying, take the square root of X function, which is the top half of a parabola, go out here to 9, and find that slope. Okay? Now, so that was the first part. What they want you to do is identify what f of x was and identify what a was. That's what we're doing. So it's kind of like we're going backwards on that. Okay? Now, they said, examine a graph of the difference quotient. Now, this is something we're going to do later, so I'm not going to bother with it right now. But what they're saying is, let's don't even pretend these are h's anymore. If we're going to graph this, of course, in your function graphing mode, you got to plug in what? X's. So we would take this delta x and just make it an x. And so we would just graph the graph of 9 plus x minus 3 all over x, and we would just graph that. Now, it wouldn't be this graph. This is a square root graph. But we would graph this graph. It'd be some weird graph. Who knows what it is. And we would look at that as the x was getting close to 0. So we would just trace near 0, and we'd see what the value is. Okay? And it ends up coming out to be, positive, real small positive value, because it'd be the slope. But we'll get into that later. Okay, so what about this one? This one also is f of a plus h minus f of a all over h. Of course, it's still got the h. And now I'd be looking at this, and I'd be saying, okay, well, what's my a? Well, it's the first thing here's got to be something plus h. Well, what would that a be? Got to be 0. This is 0 plus h. And then that means this would be cosine of 0, right? F of a. Well, what's cosine of 0? 1. Just like over here, this is square root of 9 plus x, and then this would have been square root of 9. F of a. Square root of 9 is 3. So that's why there was a 3 there. Okay? This is cosine of 0. So this is cosine 0 plus h minus cosine 0 all over h. So this is the cosine function, and we're doing the derivative at 0 because of that a value right there. Well, think of the cosine function. That's an easy one. What's the slope at 0? 0. 0. Okay? So that's 34 and 35. We're going to get into that a little more later on. All right. Okay. Here's a new thing for today. So let's get into our notes here. And so here's what we would like to do. You don't have to write this down, but does this look familiar? Remember this from yesterday? But I got news for you. This is not the same as yesterday's. It's just a teeny bit different. What's different? Instead of, what did we have right here? What was this number? Or what was this letter? A. And then this was a plus h. And this was a, and this was a plus h. But otherwise, it's the same thing, right? Otherwise, same thing. 2 points becoming 1. So it would be this right here, right? So to be honest, this is the version we're going to use. Now, see, here's where that alternate version with x and a as my 2 points don't work very well, because all that does is let x get close to some point a. What this is going to allow us to do is this is going to allow us to let x be any x. And you could say, well, a could be any a, and that's true. But we're going to go ahead and do this. Instead of find f prime of 3, like we were doing our homework today, or f prime of 4, we're going to say, let's find f prime of x. Okay, so write this down with me. So here's my x squared. Here's f prime of x. So let's go through it. So f prime of x is going to be f of, I'll let you catch up here, f of x plus h minus f of x all over h. So when we talk about the definition of the derivative, the limit definition of the derivative now, we're actually talking about that right there, instead of f of a plus h, right? And that's fine, f of a plus h, that just lets us find that a typically represents just a specific point, like 3 or 4. But now x is going to represent any and all points, right? So we're going to leave that x in there instead of put a 3 in there. We're going to see what happens, okay? So, what do we got? Well, what's f of x plus h mean? That means put an x plus h in for the x. So what do we get? X plus h squared minus, what's f of x? X squared all over h. Right? With me? Okay, so it's the same thing as yesterday. It's just instead of 3 plus h, or 4 plus h, or 5 plus h, we're just going to do x plus h. Okay? So what's x plus h squared? Well, that would be x squared plus 2xh plus h squared minus x squared all over h. Then what? X squareds cancel. Can I take out an h? I'd have 2x plus h all over h. Again, the h's cancel. I have the limit as h approaches 0 of 2x plus h. And so what can I do then? I can put a 0 in for h. And what do I got? So you're telling me that f prime of x is 2x. So if f of x is x squared, f prime of x is 2x. Now, I'm going to do a quick little chapter 1 thing. Right? Wouldn't that be 2x right there? Agree with that? Okay, and the black here would be f. Let's think of the chart here a minute. Think of the chart. When right here, the slope is 0. The blue graph changes from negative to positive. What's that mean? F has a local min. When f prime goes from negative to positive, f has a local min, yeah? F is always concave up. What's that mean f prime is? Increasing. Oh yeah, increasing. Seems to fit all those things we talked about. Makes sense. We just found a new rule. If f is x squared, f prime, and I think we did one of those, well maybe we didn't do for that particular one. So what's the slope at 3? What's the slope at 4? Slope at 5. Isn't that nice? Okay, maybe we can find something interesting happening here. Okay, let's try this one. What if f of x was x cubed? We want to find f prime of x. Well, limit h approaches 0, f of x plus x. I just always like writing this out. I just like writing the definition out first. And just less chance of screwing up. But when you're doing your homework, if you've got several of these to do and you don't want to spend a lot of time, on that, that's fine. But now we're gonna plug x plus h into there, so that's x plus h cubed. Minus x cubed all over h. Okay, now here's where Pascal can come in handy. Okay, this will save me a little bit of time here. So x plus h cubed is going to be what? 1x cubed plus 3x squared h plus 3xh squared plus h cubed. So 1331, right, on Pascal's triangle. Just saves me a little time. Now, probably not on the quiz, If there is, the highest I would go as an x cubed, and if you just had to do x plus h, then x plus h, get that, then do x plus h, fine. If you don't remember Pascal's or don't want to use it, whatever. And then don't forget the minus x cubed at the end, all over h. And what's happening? X cubes cancel, which is a good thing. And what do we got? We got stuff that all has h's, so we can take out an h. What do we got? 3x squared plus 3xh plus h squared, all over h. H is canceled. We're left with 3x squared plus 3xh plus h squared. As h goes to 0, isn't that going to be 0? That going to be 0? What's our answer? So you're telling me that f prime of x, if f of x is x cubed, f prime of x is 3x squared. Check that out real quick. 3x squared would be something like that. X cubed, of course, comes up, then does this, and then does that. Right? So let's think about f prime. F prime positive, but getting less positive, and then it's positive and more positive, right? So f prime is positive, then stays positive. What's that mean f has? Flat spot. These slopes are positive, but they're getting less positive, and then they're positive, get more positive. Makes sense, yeah. F prime decreasing means this is concave down, then f prime increasing means it changes the concave up. All looks good. Some of you guys have noticed that though already. In the Desmos, when we look at an F graph and match it with an F prime graph, didn't you notice that it looked like a fourth power was the F prime was a third power? You notice that? Or if you had 3 humps, if you had 3 humps on F, then the F prime had 2 humps. Didn't that always seem to be the case? All right. Now, oops. So now, well, this is so much fun. Let's just do x to the 4th. Oh, wait. You know what? It's not that much fun. How about we just write down what the derivative is? 4x cubed. See, this is one of those type of books. What's the derivative of x to the 9th? Are you kidding me? All you have to do is bring the power down in front and drop the power by 1. And that came from Pascal and slope. Let's don't ever forget where that came from. That came from slope. That was a slope formula. That was just 2 points, x and x plus h, and we did the slope to it, and it came out that nice. Unbelievable. That never fails to me. Look at that. That is crazy. Look at this one. Yeah, it dropped down to 1. We bring the 2 down in front. We drop that to a 1. That is called the power rule for derivatives. And we're going to use our new Leibniz notation to write it. And we're going to say this. If I have x raised to a numeric power, so this is an x raised to a numeric power, and I'm doing the derivative with respect to x, then you're telling me the derivative is what? n times x to the n minus 1. The power rule for derivatives. That's a great shortcut, right? Hey, you see why we call the definition the long way, right? You're going to do it the long way some more, but, right, that for now, for a little while here, but we're also, your homework tonight's going to be a lot of shortcut ones. There are a couple I'm going to want you to do with the definition the long way, okay? But that is a really nice, handy little rule for derivatives, okay? And it works for not only just numeric, but if you had square root of x, which is x to the 1/2, right, that would work. You can still do that power rule. You bring that power down in front, and you subtract 1 from the power. It works for negative power, okay? All right, let's do a little bit of discussing here. Again, let's put this in our notes. So let's add into this. Let's add into this. What about our shifting and our stretching and our compressing stuff? How does that affect the slopes? So if we're going to want to, because not every function we deal with is going to be x squared or x cubed. They're going to be more complex than that. So how does this affect? Okay, so let's talk about what if we had an x to the 5th, but we shifted it to the right 4. How would that affect the slopes of the x to the 5th graph? Would it change those slopes at all? Would it change the steepness of that graph? But it would change where they were, right? So like if you had an x to the 5th graph and there was this place where it was like this steep, that would be now shifted over 4 units, right? So your derivative equation, isn't it still going to have to be shifted over, right? It's just, right? So we'll bring down to 5. We'll leave the inside alone. You'll hear me say that a lot this year. Turns out we always leave the inside alone. When we do the derivative and there's some stuff on the inside, we leave the inside alone. The inside stays the same as the original function. So we bring the 5 down, we drop the power to a 4, but we leave the inside alone. Okay, here's another one. We got a 6 power, and we got a 3 multiplied in there. Now what's that 3 on the multiplied on the inside do? Doesn't shift. It's a stretch or compress. Which is it? When it's on the inside, it's the opposite of what you think. So the minus 4 actually goes right, not left, right? So a 3 on the inside actually compresses by a factor of 3. So now that changes 2 things. That changes where those slopes are. They're now squeezed in. So that's why we're going to leave that 3 on the inside when we do our derivative. But what else happens to those slopes? Are they the same? They're steeper. By what factor do you suppose? A factor of 3. So not only do we do where the slopes are changed, if there was a slope out here at 6, that slope's now in here at 2, and that slope is 3 times as steep. So we need that 3 in 2 places. So we need to keep the 3 there. So we're going to bring the 6 down in front. We still got to do our derivative rule. So we're going to bring the 6 down in front. We're going to leave the 3 in there. We're going to drop that power to a 5. And we're going to multiply by a 3 because those slopes are 3 times as much. We're going to, you'll hear me say a lot, we're going to kick out that 3 on the inside. And so if you're multiplying by something on the inside, you got to kick it out. You leave it in, and you got to kick it out and multiply by it because it's compressing and making those slopes multiply by that much. And so we would probably simplify that then and go 18 and then 3x to the 5th like that. Okay, so that's a little tweak there that we got to keep in mind. So we've already talked about sine 2x. What's that 2 do? It compresses, right? So what's the derivative of sine? We already know. Cosine. We're going to leave the inside alone. We always leave the inside alone. But then we're going to kick out a 2. Now, normally we would just stick that on the front then. But we're going to kick out a 2 because that compresses that graph, and it makes those slopes twice as much. So we got to multiply those slopes by a 2. Okay? What about this 3 on the outside? What's that do to the graph? Vertical. So what's that going to do? Isn't that going to stretch those slopes? So when you're multiplying on the outside, it just hangs out there. We just leave it there because we need it, because it's going to multiply those slopes. So it's just going to hang out there, and the derivative of sine is cosine. So if you got a number multiplied on the outside of some function, it just hangs out there, and then you do your normal derivative. Okay? Just like 7x. Well, this is such an easy one. It's a line. What's the derivative of 7x? 7. It's always got to be just 7. The slopes are always 7. But it is like doing the normal rule. You got a 1 here, so we would bring the 1 down in front. 1 times 7 is 7. We said the 7 just hangs out there. And then it'd be x to the 0. What's x to the 0? 1. So just 7. So that any linear, if you got 3x, the derivative's 3. You got 4x, the derivative's 4. You got negative 2x, the derivative's negative 2. The x just goes away because it's going to go x to the 0 and it'll just be gone. But it's a line, so it should have that slope. Okay, what's the derivative of 5? That's a horizontal line, so it's got to be 0. But if you want to think about the rule, it would be this. You could put an invisible x to the 0 on there, and then you could bring the 0 down in front, and then, of course, that's going to wipe out everything. So it's just going to be 0. Okay? So we usually don't do it, though. The derivative of a constant is just 0, right? Because it's a horizontal line, so the slope should be 0. Okay, let's do a couple more here. So what if you had 1 over x cubed? Sometimes we have to rewrite these so they fit our rule. So 1 over x cubed is x to the negative 3. Now, what would our derivative be? Negative 3 x to the negative 4th. Make sure you subtract correctly. Negative 3 take away 1 is negative 4. Now, in algebra class, Ms. Andreessen hated for you to leave it negative powers, right? There's reason for that. There's times we're going to want to shift it to a positive power, so we do work with it. But for right now, just for our answer, we'll just stop right there. That's good enough. Now, if we had to do some stuff to it, like plug in some numbers or something, then we'd want to flip that down to a positive power. But for us right now, just leave it right there. Okay, what about square root of x? Well, that's x to the 1/2. So the derivative of that is 1/2 x to the negative 1/2. 1/2 take away 1 is negative 1/2. So you can see why in calculus we don't like to use radical form very much. We like to use fractional powers. We like to use powers, okay, because of this rule. It's so powerful. X to the, what's cube root of x to the 4th? 4/3. The root is always the denominator. So 4th root, or the cube root of x to the 4th is x to the 4/3. So that would be, derivative would be 1/3. 4/3 x to the 1/3, right? 4/3 take away 3/3. 4/3 take away 1 would be 1/3. Okay, what about if you have some stuff strung together here? What's your guess at what this derivative would be? What would common sense tell you can do? Common sense isn't always right, by the way, but just do it for each one, and it turns out you can. So what's the first one? 12x cubed minus 6x squared plus 0 goes away. What about this one? X to the 3rd times x to the 4th. We want to do the derivative. What do you think? X to the 7th is a derivative, or you have to make it x to the 7th first. Now, here's why I put this one on here. Common sense told us we can just do each one of these individually and just string them together. Turns out that's true. So the question here is, could I do this derivative and this derivative and then multiply? Well, let's try it. Let's see. One way we know should work for sure is we go ahead and we just make this x to the 7th, right? I thought I heard somebody say x to the 12th, but I'll pretend I didn't hear that. We have the power train. That'd be x to the 7th. So we know that's true. And we know the derivative of x to the 7th is what? 7x to the 6th. So we know that should be the derivative, for sure. So what if we tried what we were thinking maybe? Could we do that derivative and then do that derivative and then put them together? Oops. Doesn't seem to work. That's 12x to the 5th. That didn't work. So the answer to that is no. So if you've got functions added or subtracted together, you can do their individual derivatives. You can do the derivative of each term. But if you've got things multiplied together, you can't do their individual derivatives. So that takes us to this one. Our guess would be, if we hadn't just done that last problem, by the way, because now you're probably wondering, let's pretend we hadn't done that, and I threw this at you, most people would just say what? 3x squared cosine x, right? Okay, because of what we just saw on the last page, right? Because of what we saw on the last page, we can't do that. If you've got two things multiplied together, you can't do their individual derivatives and multiply those together. It doesn't work. Okay? So, stay tuned to chapter 3, and we will figure out how to do that. Okay? All right. So, that's this new shortcut for derivatives. Very powerful. Allows us to do a lot of different types of functions, but not all types of functions, right? As we can see right there. So, we'll have to figure out some other stuff or something like that. Okay. So, homework. And this is what it says, the next two lines on your homework. We're going to do the two homework questions. A lot of those are using the shortcut. So if it doesn't say use the limit definition or the long way or whatever, if it just says find f prime or find a formula for f prime, then it's what we were just doing. It's this step. So if they're giving you these functions and they want you to find f prime, it's just the shortcut. Right? This rule, what we were just doing. Now, there are two that I want you to do. Now, both of these we could do the shortcut with the power rule, but I want you to do both of these the long way. Why? Because this is going to get a practice bow tie, and this is going to practice that conjugate thing I showed you. This is going to practice bow tie, and this is going to practice that conjugate method I showed you. And then you're also going to see that, hey, yeah, it matches up with our shortcut rule. Okay? Yes?
You're saying whenever those come up in the homework, you do them along the way?
No, these aren't going to come up in the homework. These are separate. These are separate. So, two homework questions. I don't think there's any in there in those homework questions that tell you to do it the long way. I don't think. There's some questions about rotation. There's several questions that says find a formula for f prime. Find an expression for f prime. That's this stuff. That's what we were doing here, the shortcut. Find a formula, find an expression for f prime. So that's using this power rule. Okay, the only two I really think you have to do the long way. I'm just pretty sure none of those say that. Are these two I'm giving you here? So those are the two extras to do. Okay.
So we only do the long way if it tells us in the directions.
Exactly, and that's what will happen on the quiz. Right, the long way is the limit definition. If it says use the limit definition, that's the long way. Okay.